We saw that this particular expression, if I take this as f of x, so for f of x at x is equal to, actually this is what it means, for x is equal to 2. That is, in place of x, if I substitute 2, sorry, not 2, in this case a, what happens? We get 0 by 0 clearly. But the limit turns out to be, as the value around this particular value, the function's behavior turns out to be this. Right? This is something that we derived. So the limit, it exists around this value. We have a particular output for x is equal to a minus some value, right? Minus or plus some value. At a, at x is equal to a, we have the output to be indefinite. Now, this was algebraic expression. We have a similar stuff happening in trigonometric expressions. Say this is h of x. Clearly, if I happen to substitute x is equal to 0, what happens? 0 by 0. Again, it's undefined. But if I happen to push x out and around the value of 0, how will it behave? The output will be equal to 1. Limit is of x by x, as x tends to 0, the output will be equal to 1. Okay, yes. So how will we derive this? Here too, one thing we can conclude is, yes, the limit does exist and we need to derive this. To derive that, we need to make use of two theorems. This is theorem 1 and this is theorem 2. So what does the first theorem tell? Let me explain that with the help of this graph actually. We have g of x and h of x. G of x is this blue line and h of x is this orange line. Now, g of x is clearly all the time greater than h of x. Do you guys agree? Right? For whatever value we take, -2, 0, any value over here within this range, g of x is always greater than h of x. The theorem tells a very commonsensical thing. If it's so, if g of x is greater than h of x, right? If g of x is greater than h of x, if it's so, then the limit also will have a similar relationship. For example, if I happen to push g of x and h of x near 2. So let's see what are the values. You can see the values. The x coordinate are the same. We can see that the y coordinates in g of x, it's obviously more than h of x, right? So limit g of x, just a second, I think I flipped. Here g of x is greater than h of x, guys. So let me change this off, just a second. So if we have two functions, let f and g be two real valued functions with the same domain, such that if g of x is greater than h of x, right, we have this particular condition. For all x in the domain of the definition, for some a, if both of this they exist, which it does, then we can see that limit g of x as x tends to a will be greater than or equal to limit h of x as x tends to a. Okay, so in this case, limit x tending to 2, and we have limit h of x as x tends to 2, right? So what we have here is, we have 4.67. We have this value to be 4.67 and this to be 3.67. So we can see that this two here will have a similar relationship. Okay, whatever the relationship the function has, a similar relationship will also be established between the limits as well. Commonsensical stuff, right? Okay, next. The second theorem, what it deals with is, we have three functions. So those three are g of x, f of x and h of x. So here clearly g of x is always greater than f of x and f of x is always greater than h of x. So this is the relationship. Now what the function talks about is, again here 2, I need to flip things around. Just a second. So we have three functions, g of x, f of x, and h of x. G of x is always greater than f of x, and it's always greater than h of x. By chance, if we have the limit of g of x where x tends to a, if it's equal to a constant, and we have limit h of x as x tends to the same value a, and if both of them tend towards the same answer, that is, we are getting the same answer with both of them, then what can we conclude? What about f of x? What will happen? So by default, okay, without any calculation, we can conclude the following. So what is that? We have limit of f of x, the middle wala limit. If it's tending to the same thing, by default it will be equal to the same answer. You'll get the same output. The reason being, as f of x is sandwiched between h of x and g of x. So the example is clear over here. We have g of x, h of x, and f of x. So g of x is more than f of x, which in turn is more than h of x. Agree? Right? Now you can see the x coordinate, they are the same. Look at the y coordinates. We have greatest in the middle and the lowest. If they approach, if the first and the third one, if they approach the same value, look at the middle value, what happens to that? Right? Now it is 0.01, 0.01, and of course they are not the same, it's minus and this is plus. Can you see that? Both the first and the second one, third one, it reached 0. By default, the middle one has to reach 0. Okay, so this is your sandwich theorem. The value of f of x, it's sandwiched between the first g of x and the second h of x. It's between that. If g of x and h of x has the same output for a particular input, then f of x will also take up the same value. This is the theorem. So now you guys can pause and have a look at the following things.